Embodied online inference is the operational baseline for autonomous agents in the physical world. A system navigating a volatile environment must process sensor data, make decisions, and learn from its mistakes continuously without ever going offline. The standard machine learning approach to learning is batch propagation. An algorithm accumulates a specific number of inputs, pauses the forward flow of inference, and runs a computationally heavy backward pass to update its weights. This creates a paradox for real-time agents. Pausing the system to calculate how to navigate the environment requires the agent to temporarily go blind to that environment. Because of this architectural blind spot, the standard industry metrics we use to evaluate AI, like raw throughput and static accuracy, are highly misleading when applied to edge deployment. To find an architecture that actually survives continuous operation, we evaluated 5 distinct training modes against 2 highly volatile environmental benchmarks. We analyzed raw accuracy alongside the specific windows of system availability. In a dynamic physical system, a neural network with slightly lower raw accuracy but 100% continuous availability will always outlive a highly accurate model that blinks. We start with the industry standard, NormalBP. The network processes a full forward pass and then halts for a periodic batch backpropagation update. In test 41, a target sine wave abruptly shifts frequency. The secondary line, NormalBP, attempts to track it but suffers a 118 millisecond latency spike, producing 0 outputs. Zooming out, NormalBP is blocked and blind for 9 of the 10 seconds. This causes regime lag. The network's accuracy spikes after the environment has shifted, as delayed batch updates optimize for previous states. Neural architectures relying on batch pauses cannot be deployed to the edge. Theoretical accuracy is irrelevant if the agent is paralyzed while calculating it. A theoretical fix is StepBP. Instead of waiting for a batch, the system forces an immediate backpropagation pass on every single forward step. In the Sine-wave benchmark, StepBP never stopped serving inference. It recorded 0 milliseconds of blocked time and achieved 100% availability. This matrix represents test 17, where the agent's goal flips from chase to avoid and back in 5-second intervals. At the first inversion, StepBP's accuracy skyrockets to 100%, but at the second change, it violently collapses to 0 and fails to recover. Calculating gradients on every tick overfits to the current state. The model learns so aggressively it loses the capacity to adapt when rules change. Forcing continuous backpropagation solves the blocking problem, but it destroys the model's long-term adaptability across multiple environmental inversions. To reduce the computational burden of gradients, we can replace the chain rule entirely with target propagation, internally referred to as Tween. This schematic isolates Tween. Instead of full weight importance, by adjusting locally and bypassing standard backprop, thousands of adjustments happen rapidly without a global bottleneck. However, the standard implementation of Tween contains a flaw. It still dictates that these localized updates happen on a periodic batch schedule. In the Sine-wave test, Batch Tween produced high throughput but suffered the exact same 9-second blocking penalty, crushing its overall score to just 79. Swapping to a highly efficient algorithm yields no operational benefit if the system's foundational architecture still mandates a stop and batch scheduling pause. Solving the embodied inference problem requires a systemic fix at the architectural level, abandoning the sequential network sweep in favor of a step mesh. This 3D volumetric grid represents a double-buffered system. On every clock tick, all layers fire simultaneously, swapping data into new buffers. Separating read and write states lets the network update weights every cycle without interrupting the forward inference stream. When we combine this continuous double-buffered mesh with the layer local efficiency of target propagation, we get a new mode, StepTweenChain. In the test 17 finale, NormalBP, StepBP, and Batch Tween all crashed to 0 accuracy at the 11-second mark. Only StepTweenChain maintains non-trivial accuracy. It takes a minor hit but immediately catches itself and recovers rapidly. Pairing a continuous step mesh with layer local target propagation creates a resilient architecture that tracks moving goals, adapts rapidly, and never goes offline. When designing autonomous agents, prioritizing raw throughput and peak static accuracy creates blind, brittle systems. The evaluation standard for embodied online inference requires a new metric, the availability weighted score. Notice how the availability percentage acts as a strict penalty multiplier. It ruthlessly filters high-accuracy models, punishing any architecture that requires blocking time to learn. In the final logs, models that process on a per-step basis achieve scores in the thousands, while batch-dependent modes are relegated to double digits. Training scheduling, the decision to batch or update per step, serves as a first-class systems architecture decision. Whether a model blocks or remains inline dictates its capacity for survival. To build AI that survives, in the physical world, we must discard batch metrics. The edge requires continuous, layer-local architectures that keep their eyes open.